Well, thank you very much for the introduction and for the applause. So I'm going to be talking about how to develop, or how we've been developing, an XR user interface for high-level robot teleoperation. And before I start talking about that, I just want to put this in context of some of the work that we've been doing over the past decades, some of which I've actually reported on in previous AWEs. So we've been for a long time interested in remote task assistance, how one person can assist another person when they're not in the same place. And the images you're seeing over here are from a demo that we did at SIGGRAPH, frighteningly some 7 years ago, in which we were looking at having a local technician working in AR, through an optical see-through head-worn display, in front of the equipment that needs to be maintained, being advised by a remote subject matter expert working in VR. And in that project, we actually, in the demo we gave, we had people from the arbitrary SIGGRAPH attendees being able to walk up and actually try our system out. Now, this is person-to-person communication. For example, the SME might even be at home if they have the right equipment there, which I think in the future people will. The technician would be at a job site. All the instruction is really low level. We're telling people exactly what to do. That is to say, the SME is telling the person who is the local technician exactly what to do. It's all happening in real time. So I'm going to change from that to what we're working on now, or at least one example of what we're working on right now, which involves high-level, as opposed to low-level, robot teleoperation. So the idea is to have a worker at home specifying high-level goals for robots at some remote factory site or sites, using AR and VR to interact with those robots, and very different from the work that I had just described, without requiring that the worker has any expert knowledge of the robot hardware or of how to plan for robots to do stuff. So just to emphasize some of those things, high level means that we want our worker to be able to specify high level goals, not low level actions. They don't need to know how the robot or robots work. So they're going to specify in the work that I'm going to describe, in the research we're doing, a goal pose, a 6 degree of freedom position and orientation for each of a set of parts. And those goal poses will be realized by the robot or robots. Now, another important thing for us is asynchronously. That is to say, the worker should be able to specify new goals without having to await completion of earlier goals. And that means we need to have somewhere in the middle there some way of keeping track of what has been specified, how far along things are, did it work, did it not work, etc. And I'll talk very briefly about how we do those things. Just to give you an idea of what's happening in our back end, I'm working with colleagues who are robotics researchers, and our back end right now in our test bed consists of a planner which plans the actions if you specify high-level goals to it, and an actual physical robot for which the plans are being made. In this case, the work that I'm going to describe to you is done with a Universal Robots UR5 with a parallel gripper. So it can use a parallel gripper to pick things up, move them around, rotate them, translate them within the range of its reach. So one important thing for us is to note that this is very different because of the asynchronicity, because of the fact that things are being done remotely, because you're not there, from, for example, specifying in a CAD system or a drawing system that I'd like to move something from one place to another. When I do that in the CAD system, I grab hold of something in 2D or 3D, I move it, rotate it, otherwise modify it, and when I let go, so to speak, it's been done, okay? It might not be what I want, but it's been done. I can undo it, but it's been done, and I can proceed to do many more things after that. In the work we're doing here, when we end up specifying that we'd like something to be done, and it's not going to be done by us, it might not get done immediately. It might actually not work because there's a robot that might not be able to actually do it. There might not be room for the robot to move, all things that are going to be determined by a planner. And even if it turns out that the robot is perfectly capable, or the robots are perfectly capable of doing it, they might not be around right now. They might be busy doing something else. And so we need to understand, as we start proposing changes the current status of the system. So let me tell you how we do that. In our test bed, things in an initial status in which we are confident that they are in the pose that we want them to be are represented in whatever way that they would normally be represented. And in the work you're seeing over here, this is all being done in VR, so we have basically models of the parts. And in this case, that green-looking kind of truncated cone is essentially showing us a green-looking truncated cone that's at its initial status. Now, if you want to do something to it, in our work that means moving it, translating it, rotating it, then as you do the editing, as you'll see, we use this cheesy kind of shader approach where there's a little striated kind of pattern on it, which is moving, where we're assuming that real objects of the sort that we're working with would not look like that. And that's telling us that we're actually editing. At some point, the user may decide for one or more things that, gee, they really like this, and they want to propose this as a goal to the robot. Because we want to let the person be able to experiment, move things around, without wondering whether the robot's going to catch up and start moving things that they really didn't want to have moved. So having decided that they like it, they're going to send a goal. So what happens next? We send the goal to the robot, and the robot needs to figure out, or our system, backend, needs to figure out, is this something that can actually get done? So it has to be validated. And then after it's validated, assuming that it is considered to be valid, then it needs to get executed. And of course, it's not going to get, probably not going to get executed immediately, because we do not want our user to know anything about the particular robot or robots. It might be something that might take very little time. It might be something that takes a lot of time. It might be something that looks like it would take a very little time, because if I thought about myself doing it, I might pick something up and move it over there, but maybe my arm, which is a human arm, is not the same size and shape as a robot arm, and maybe the robot arm is 1 millimeter too big to fit through where my arm fits through, and it's going to have to go in a very circuitous path around that. We don't have to worry about that. So assuming that it's been validated, now it's waiting execution. At some point in time, it's going to start getting executed. We have different ways of representing this. Here you're seeing a little placard indicating the status. And as well, I'm not sure how easy it is to see, but we're also using these little halos around objects, where the idea is we're assuming that in our world, we can't change the color of something from what it really is, but we're going to assume that none of the objects we're working with actually have a little halo around them. So the halo is going to be our way, or part of our way, of communicating what's happening. And then at a certain point, the robot says, okay, I've done it. Now, do we trust the robot? And the answer is maybe not. So we need to have the user confirm. This is not something that we have been addressing right now in the work that I'm going to show you, but ultimately the confirmation, if a person is not actually there on site, is going to get done by that person looking at and otherwise perceiving sensor data that will hopefully let them know whether or not the robot is actually, or robots have accomplished their task. And at that point, the user is going to say, okay, you know, that's what I wanted, and confirm the outcome, or perhaps need to go and tell the robot to do something different to make the robot outcome the way that they actually wanted it. So we have all these different states that any given object can be in at any time. So high-level asynchronous teleoperation is not something that we've invented. A number of folks have been doing this. I'm just very quickly mentioning names without going into any details of some groups that have worked on this task in a variety of different domains. And one of the things we're particularly interested in is how to visualize what's going on, not just the state of the task, as I just showed you, but in a task that's taking place in 3D in space, how do we show basically the history, the spatiotemporal history of what's happening? And so a lot of people have worked on, including my lab, on approaches to visualizing spatiotemporal histories of many different kinds of things. For example, at the left side of the screen, we're looking at ways in which we can aggregate the information within the space, a 2D space or a 3D space. And in fact, the upper left-hand image over there from Sue and colleagues is from a 2D drawing system where the history of what's going on is represented by a variety of these little iconic meta objects. Other examples on the left, aggregating stuff in 2D or 3D space, all the rest are actually 3D space, are basically showing what's happening with a variety of different ways of annotating those objects within the actual 3D space of the task, or 2D in the case of that drawing system. Now, another approach is what we refer to as a timeline. So now we're going to use space in a way that doesn't correspond to actual physical space, classic timeline, left to right, older to newer, and we position things on that abstract representation of space to be able to indicate when it got done. So the top work on the upper, at the right-hand side of the screen is stuff that my lab did frighteningly some 32 years ago, showing the edit history of a 2D editor. And the pieces of work at the bottom are actually in 3D, showing a variety of ways of representing sort of left to right along a timeline, the history of things that got done in different kinds of tasks. So these are two interesting approaches, and a lot of what we're working on is, can we try with the same goals to come up with the use of one or both of these approaches and compare them? So what I'm going to talk about is a comparison of this aggregated approach of putting everything within the same place, the same 3D space in our case, versus a timeline approach of laying things out basically along a timeline going from one point to another in one dimension. So first I'll tell you a little bit about the work on aggregated representation. And there's actually two things that I'm going to show you, two different variants that we were looking at in our work. One I'll call static and the other one adaptive. And in the static aggregated approach, which I'll show you an example of in a couple of seconds, we are basically, as I said, putting everything within the same 3D environment. And as you do stuff, there'll be the halos that I mentioned, the little placards. And if you actually hover over with, in our case, it's a VR controller, if you hover over an object, you get more information about the state of that object. In the adaptive aggregated approach, which I'll also show you, when you hover over something, it actually will let you see what the world looked like, take you back in time to what the world looked like when that particular goal was actually specified. So not just information about the goal, but really show you literally rolling time back what things looked like back then. That's what we're calling adaptive. So let me show you what the static aggregated approach looks like. And so we have a collection of objects over here, and now we'll see a person basically specifying a set of goals. And so they grab hold of an object, and there's that editing information I was showing you, that visualization. That's now been sent to be validated. Another object, grab it a couple of times, reposition it, configure it on the side, and then we can pick up these little guys over here and stick them in place. So basically, as you're doing this, you're seeing representations of where things used to be, a line linking the former location and pose to the current one. And again, if we hover over something, as you'll see in a couple of seconds, we can see more information about each one of the goals associated with the objects that were being manipulated over there. So that's our static aggregated approach. So let's look at adaptive aggregated. And in adaptive aggregated, it's pretty much the same thing, except when you hover over something, it'll actually change the state or the visualization of the state of the world, taking you back to with the way it was when you were specifying something. And again, that, of course, could be potentially useful. So let's see what that looks like. And you'll notice some of those things are appearing and disappearing because of the fact that we're basically taking things back to the time at which those goals were initially specified. That, oh, by the way, that was running at 2 times speed in the interest of time. I showed you the first one running in real time, and now I'm going to show you a couple of things that were just sped things up in order to be able to not fill up more than the 25 minutes that I have. So one more example of adaptive aggregated. If you move something to one location and then maybe change its pose and then move it again, we're going to show, if those things actually haven't been realized yet, lines connecting the original pose to the next one, to the next one. And again, each of those represents a goal that may or may not have actually been accomplished. And so you're seeing that over here. Again, as I hover over something, we take things back to that point in time at which that goal was actually specified. So now we'll look at the timeline approach that I mentioned. And as I said, in the timeline, we're going to basically show one goal after another as it's specified in a timeline, which in our case is going to be above the area in which the actual virtual parts live. So let's see that. And also running at double speed. And so as we do each one of these things, each one of the things that we're trying to get done is going to show up in a separate little panel of this little timeline history that you're seeing. And as we hover over things there, we can get more information about each one of them, showing basically where things came from, etc. Okay, so we have several different ways of doing this, and the question is, gee, which one works the best? Maybe one, maybe another, or maybe they're equally good. And so a lot of what my lab does is when we develop things, we run user studies to get a sense of how people respond to, react to, in terms of objective things, like how much time it took them to do something, and subjective measures, like did they like it or not, for example, or even how much time did they think that it took. And if you think something took a lot less time, the old saying is time flies when you're having fun, and something that people think of as taking less time could often be something that you might get them more likely to be convinced to do, rather than something where they felt it was really tedious and slow, even if those things took exactly the same time objectively. So we ran a user study to try to validate this. Ours had 17 participants. And we had basically some 12 different conditions, 3 different views, the static, adaptive, aggregated, and timeline views that I just showed you. And then we looked at how we connected together the different poses that something might be in over the course of moving it around. So this is just using different line styles, either one in which there is a continuous gradient that goes from the oldest pose to the most recent pose, getting in this case from very dark to lighter and lighter and lighter, or a segmented one in which you go from the original position to the first pose with this gradient and then start all over again for the second position to the third, or either the first to the second, and then the second to the third to the fourth, etc., where each line has that kind of gradient along it. And then finally, we looked at 2 different tasks, both of which involved these sort of soma cube models that I'm showing you over here. One of which was assembly, so you get a whole bunch of separate pieces, and you're instructed how to assemble them, and now you're going to need to go and follow what we told you to do. Now, normally, we're assuming that the person doing this knows what they want, but in our study, we couldn't assume that, so we had to sort of make people do what we asked them to do, rather than having on their own free will to do what they wanted to, because that would make it very hard to compare things across users. And then we had another task that involved disassembling a collection of objects, pieces of a soma cube, and then assembling them when you're done. So as I mentioned, assembly and disassembly, this is what we call a within-subject experiment. That means each participant tried all of the different conditions that I mentioned. We counterbalanced the order, that is to say, we didn't do one condition always the first and another always the second. We basically counterbalanced the order, so no particular condition got used more in one position than the other. And in the stuff that I'm going to show you, the results, we were not running the planner and the robot at the same time, because what was important to us was the user interface, and to run the planner and the robot, which were not in my physical lab, someone would have to be in the other lab, things can go wrong, and those things that can go wrong basically have nothing to do with the user interface, everything to do with a problem with the robot. So we just didn't use those. So to make a long story short, some of the things we looked at were the trial completion time, and analyzing this with a particular approach called a linear mixed effects model, we're able to show that the adaptive and static aggregated views ended up being faster for performing the same task than the timeline views. And the line style approach, which I personally didn't think was going to be significant, and one of my students really wanted to try it, ended up not being significant. There was really no interestingly significant difference between how people did with one versus another. In terms of preference, on the other hand, it turned out that while people liked the static and adaptive aggregated conditions, did faster with them, they actually greatly preferred the timeline condition. And so here of the 17 people, you can see that some 13 of those people had it as their first choice. We basically asked for first choice, second choice, third choice, right, for a timeline. And there were only 2 people that had first choice for each of the aggregated conditions. So it's pretty much a very strong preference being stated for the timeline with a follow-up of the adaptive aggregated approach, but really trailing behind. So what do we make of this? Things we're working on right now include trying to combine the aggregated and timeline approaches. We think that it's not so much that one really trumps the other because there's one that's faster, at least with this single session experiment, and one that's actually more liked. And we're looking at ways of how we can combine the 2 of them together, not simply allow you to see it one way or the other way, but try to merge the 2. The actions that I talked about were very simple, 6 degree of freedom pose, just picking things up, changing their position and orientation. There's certainly lots of other things that one does with robots. Simple things being, for example, attaching 2 things together. Maybe you glue something to something else. Maybe you use a fastener. Maybe we deform something. There's lots of tasks that need to get done and that we want to be able to allow a person, again, to specify at a high level. And as well, the participants in the experiment were not really experienced with robots, with telling robots what to do. And we are looking at performing studies with users who are more experienced to see if we get a difference there. So I am going to stop at this point, acknowledge the National Science Foundation grant that funded this work and the work of my colleagues. If you're more interested in this, I'm delighted to talk to you at length afterwards. And there's a paper that was in the IEEE VR conference a couple of months ago that explains in more detail the stuff that we did. So if I have any time for questions, do I? No? Okay.